Over the last 100 million years, Earth's ecosystems have switched from those of the greenhouse world, think of a particularly sultry summer in Houston, to the icehouse world of today. Yet just what do we mean by those terms, and what were some of the details of that climate history? That's the topic of today's lecture. We know quite a lot about this shift from greenhouse to icehouse thanks to deep ocean drilling. The ocean has preserved very detailed histories of both the oceans, of course, but also land via the dust and pollen and soot from fires that is blown off the land into the ocean. And we also have a marvelous record of changing Earth environments that is locked up in geochemical records from the oceans. One of the most iconic of these records is that of light-stable isotopes, usually measured in the calcite shells of foraminifera. In particular, the record of oxygen isotopes provides an amazingly varied history of our planet, both the oceans and the continents. Oxygen exists in a large number of unstable isotopes and 3 stable isotopes, which, as you can recall, differ in the number of neutrons present in the atom. The stable forms are oxygen 16, 17, and 18. Oxygen 16, being the lightest stable isotope, is chemically the most reactive one. Oxygen isotopes are fractionated strongly in calcite and other minerals as a function of temperature at which those minerals grew. For example, oxygen 16 becomes relatively more abundant in foraminiferal calcite than its natural seawater abundance when foraminifera are grown in warm waters. Being highly reactive also means that oxygen 16 is more likely to enter the vapor when water evaporates than the other forms of oxygen. Those 2 features of oxygen isotopes, namely temperature-dependent incorporation into minerals and differences in propensity to evaporate, turn out to be extremely useful. From them we can deduce a whole host of things. We can figure out, for example, how warm the ocean was, the oxygenation history of the oceans, the cycle of ice sheet growth and decay, the aridity of the land surface, and the kind of vegetation that existed on land. An amazing list. So here's how we do that. Oxygen isotopes turn out to be one of our principal Earth thermometers, for example. We use the ratio of the heavy sluggish isotope, oxygen 18, over the lighter, more reactive isotope, oxygen 16, to produce what's called the Delo-18 ratio. Like carbon isotopes mentioned near the start of class, this ratio is compared to a standard value of some sort. But we get the idea of what the ratio means by just considering oxygen 18 in a ratio over oxygen 16. For instance, under warm conditions, the calcite made by microfossils like foraminifera will preferentially incorporate more of the reactive oxygen 16 than oxygen 18 relative to their natural abundances in seawater. Here, the temperature is producing the fractionation effect, not the biology of the foraminifera. The reactivity of the 2 isotopes is fairly similar under cool conditions, but when it's warm, oxygen 16 is much more reactive than its heavier cousin. Hence, the amount of fractionation between them is much lower when a foraminifera is growing calcite in cold water than is the case when it's growing in warm water. The result is that negative Delo-18 ratios, also called light ratios, indicate growth of shells under warm conditions, and more positive ratios, or heavier ones, reflect shell growth in cool conditions. We can see this effect by looking at the Delo-18 of foraminifera caught in surface net tows, where we know the water temperature that they were caught in. You can see that the Delo-18 of foraminifera tracks the water temperature with the heaviest ratios in the coldest water. Since the surface ocean is almost always much warmer than water at the bottom of the ocean, the Delo-18 values reflect this overall temperature gradient in the ocean. A really useful fact. To put our knowledge into practice, here is the oxygen isotope ratio of the calcite shells of benthic foraminifera over the last 115 million years. Because these are benthic foraminifera, the temperature signal reflects the temperature of the deep ocean. It turns out that the deep water is the coldest water in the ocean because most of it forms at the poles. So the record is effectively that of the coldest parts of Earth at any given time. Now you immediately notice that the oxygen isotope ratio 100 million years ago is much lighter or more negative than is the case today. The deep ocean was much warmer in the Cretaceous than in more recent times, reflecting that greenhouse climate of 100 million years ago. If we translate the oxygen isotope scale into temperature, you can see that the Cretaceous deep ocean was perhaps 15 to 17 degrees warmer than now. The coldest seawater in the world today is just a little below freezing, and is kept from actually freezing by having salt in it. It's seawater after all. But the Cretaceous temperatures were very much like those of offshore La Jolla, California, where I live, in the wintertime. You need a wetsuit, but the waves are perfectly surfable. Just imagine that the poles were that warm in the geologic past. Furthermore, if the polar ocean was as warm, say 100 million years ago, as La Jolla is today, then there'd be no trouble in supporting extensive forests where today we have ice sheets. We can divide that last 100 million years into the greenhouse world before around 47 million years ago, and the Icehouse world after 34 million years ago, with what's called the Doubthouse in between. This is a somewhat arbitrary designation, since you can see that the isotope record bumps up and down, but the basic idea is that the greenhouse world is warm enough to support polar forests, while the Icehouse largely has glaciers on the high latitudes. The Doubthouse is a period when we still have debate about the size or existence of polar ice masses, or they're not established everywhere. The greenhouse world was hot and sultry and supported much different ecosystems than today. Oxygen isotopes and other temperature proxies suggest that tropical surface oceans may have been routinely about 35 degrees centigrade. In contrast, the warmest places in the oceans today are about 29 degrees centigrade, so quite a temperature difference. These downright hot ocean temperatures in the Cretaceous were not at all good for coral reefs, at least not as we know them. One of the signs of coral bleaching in the modern world, for example, is that the ocean is unusually hot for a few weeks in late summer. In the Cretaceous, the ocean temperatures were routinely way over this thermal threshold for coral bleaching. So, while there were corals in Cretaceous seas, the main framework builders were bivalves called rudis that could apparently handle the hot ocean just fine. It may be that corals were outcompeted by rudis, who could grow faster or more continuously than the corals in a hot ocean. Now, after the KPG extinction, rudis reefs were driven extinct, and they were replaced by coral reefs. These last until the early Eocene warm period around 50 million years ago, when the corals once again become disadvantaged by hot ocean temperatures. Reef-building corals vanish from former reef tracts and atolls to form what I've called the Reef Gap, from about 56 million years ago to 45 million years ago. Possibly it was too warm for symbiont-bearing corals and they simply stopped building reefs. During the reef gaps, the reefs are replaced by carbonate banks made out of larger benthic foraminifera and calcareous algae. This may be a harbinger for the future, since we can already see that bleaching of corals today allows calcareous algae to take over on modern reefs. The isotope record shows that climate began to cool in the Middle Eocene around 48 to 49 million years ago. There are mummified forests about 45 million years old on Axel Heiberg Island at 80 degrees north latitude. The fossil wood can still be burned. There are also extensive Paleogene coal deposits of temperate forests all around the Arctic Circle. The Arctic Ocean was a seasonally productive marine basin thanks to 24 hours of sun in the summertime. But by 47 million years ago, diatom assemblages in Arctic drill cores show that sea ice started to form in the wintertime. Eventually, glaciers became established on Antarctica and on Greenland about 34 million years ago, and the Arctic developed a permanent ice cap based on the presence of glacial drop stones and ice-rafted debris in offshore sediment cores. Now, modern ocean ecosystems are established over, as it turns out, a considerable period of time, starting in the greenhouse of all things. The first whales and sea cows, for example, appear right in the warmest parts of the reef gap. Penguins, of all things, also evolved 60 million years ago as human-sized birds, probably eating fish and squid in coastal waters before the whales evolved. Big penguins were later outcompeted by small whales in open ocean waters. Whales themselves become fully pelagic by around 30 million years ago, with the evolution of baleen that allowed whales to strain tiny zooplankton and small fish out of seawater. However, the first baleen whales were probably not plankton eaters, but more like the modern bottom-feeding gray whales that eat amphipods and worms by filtering out bottom sediment. Coral reefs, notably enough, return in abundance as the oceans start to cool off. We tend to think of reefs as tropical systems, and of course they are, but they are much more extensive in the comparatively cool tropics of the late Cenozoic than in the greenhouse climates of the Cretaceous. Finally, there's a major radiation of marine vertebrates in the Icehouse period, with diversifications of dolphins, seals, tunas, and seabirds in the last 10 to 15 million years. The seal radiation includes many ice specialists, like ring seals and harp seals, associated with ice shelves or sea ice, as well as deep-diving species like elephant seals that were exploiting the oxygen minimum zone. Eventually, really big whales turn up by about 4.5 million years ago. The great whales like blues and fin whales are geologically very young. Indeed, it was only 7 million years ago that the biggest whale was my namesake, something called Norris anima. This is a 3D cast of it. That was about the size of a humpback. Big for sure, but not one of the recent giants. Whale paleobiologists speculate that the large body size of whales is a product of the development of modern upwelling centers that produce rich supplies of fish and krill to support Earth's biggest mammals. A really big body, as it turns out, pays off when you have to routinely swim from California to the equator to find those food patches, much less to swim from California to Chile. So in summary, the oxygen isotope record shows that the Earth cooled off in fits and starts out of the Cretaceous greenhouse. The greenhouse was really warm and probably much more humid and hot than the summer day in Houston. We have echoes of our potential future in the Reef Gap, when the ocean is too hot for corals, and when foraminifera and calcareous algae take over. We also see that many modern clades, like whales, sea cows, and penguins, got their start when the planet was still in a greenhouse state. The warm oceans come in with polar glaciation starting between 35 and 45 million years ago. There was also a huge expansion of reefs and the first occurrences, surprisingly recently, of the great whales. In the next video, we see what happened.